So, ladies and gentlemen, good morning. Welcome to the webinar Vibration Isolation Theory and Transition to Acoustical Isolation. I'm Alessandro Schiavi from INRIM, and I will be the presenter of this seminar. This seminar, as you probably know, will be held in English, and but if there is some questions, for example, from the auditory, that can be posed also in Italian, we can translate. We can translate this in English at the end of the webinar. So the webinar will be is scheduled for more or less 50 minutes, and after we can have 10 minutes for questions to the speakers. And if there is some problem in translation, we are helped by a colleague from the United States that help us in translate from English to Italian and vice versa. And also I can help you. And so we can start with the seminar. The speakers of the seminar are Douglas Valerio and Jim Sadler from Mason Industries. And the seminar is Vibration Isolation Theory in Transition to Acoustical Isolation. Please, the floor is yours. Thank you for attending.
Thank you very much. My name is Jim Sadler. I started with Mason back in 1990 as a staff engineer and currently serve as Vice President of Sales. I'm joined by Doug Valerio, President of Mason Industries, who's been with Mason in various capacities for
41 years.
41 years. His assistant, Kathy Eckhoff, who in addition to being Doug's assistant, speaks Italian. And off screen, our producer and IT assistant is Nick Furman. We're speaking to you from our United States headquarters in New York, where we have approximately 190 employees, both in production and support, both engineering and staff. Before we jump into the technical aspects of the seminar, just a little bit more about Mason. We produce vibration isolation materials primarily for HVAC equipment. We manufacture seismic restraints for that equipment. We manufacture architectural systems, floating floors, walls, and ceilings. We isolate entire structures on both springs and rubber bearings. I'll be talking about some of the fundamentals, and then I'll hand it off to Doug to discuss some of the more complex projects we've done over the past few years. I have to apologize in advance. I do not speak Italian. My apologies to the group. So just some photos. Just some photos from our facility. The first photo shows steel frames that we're providing to the computer chip facilities that have been popping up all over the world. Obviously very vibration sensitive. The steel frames shown in the photo are actually half frames stacked vertically. So each one of those frames will be bolted together to support a huge exhaust fan. They have tremendous exhaust requirements at these facilities. And again, they're extremely vibration sensitive. Some spring isolators we provide to isolate both the piping and ductwork at these computer chip facilities. Very high deflection to yield excellent vibration isolation efficiency, which we'll discuss a little bit more in depth as we go on. Just an interesting project. This was obviously a very large isolator that will support or supports a helicopter landing pad on top of a hospital in California. So not only were they concerned about the vibration and possible impact of a helicopter landing on top of the hospital, we also had to be concerned with the seismic restraint. California being a very high earthquake risk area, as is Italy. And we'll touch on that later in the seminar. We manufacture large elastomeric flex connectors with a sister company. This is a 3-meter diameter rubber flex for pipe. This was produced for a nuclear power plant in the southern United States for a cooling water for that plant. We have extensive testing capabilities here. This is a stainless V-loop. These are largely provided to data centers where they have a chilled water line connected to multiple cooling air handlers suspended above the computer banks. So they're very concerned about nozzle loads, who are able to pressure test these connectors and determine the spring rate, just one of the many testing capabilities we have. So now we'll jump into the technical aspect of it. We'll discuss vibration isolation in a little more depth. So if I have a very small piece of mechanical equipment, a very small fan with a massive unbalance, and as that mass rotates around, it wants to push the fan into the structure. As it rotates up, it wants to pull the fan off the structure. And that up, down force creates vibration, which can be aggravating in its own right. But more commonly, that vibration will radiate to an architectural element and create airborne noise. Okay, so what we want to try to do is isolate that equipment to reduce the vibration force reaching the structure. So the performance of isolation is governed by this relatively simple equation called the isolation efficiency equation. And it tells us in a simple percentage how much vibration energy we're keeping from getting into the structure. And it's only two equations in this whole presentation, I promise. This is the first of two. So efficiency is 100, which simply makes it a percentage, times 1 minus 1 over FD over Fn squared minus 1. So the two variables, F sub D, that's the driving speed of the equipment. That's the operating speed of the equipment. The F sub N is the natural frequency of the supports. And of course, natural frequency is what any system wants to oscillate at when we put it into motion. So that ratio of driving frequency to natural frequency, that's the critical ratio. And at about a ratio of 3 to 1, where the driving frequency is 3 times as great as the natural frequency, we achieve a 90% efficient isolation system, which means if that piece of equipment, let's say, creates a 100-kilogram load on the structure, if I put it on isolation that's 90% efficient, the structure is only going to see 10 pounds of that load. Okay. So again, driving frequency, very simple. We simply read that off the equipment print. Natural frequency, a little bit trickier. And we find that the natural frequency of any isolation system is dependent on how much the isolator deflects under load. And it's governed by the equation there. F sub N is a 940 times radical 1 over the deflection in millimeters. So if I put a piece of equipment or any force or any load on a spring and I deflect it 25 millimeters and I give that system a push, it's going to want to bounce up and down 188 times in a minute. If I deflect the isolator down to 50 millimeters, that natural frequency drops to 133 cycles per minute and so on. If I bring it up to 125 millimeters, that that natural frequency drops to 84 cycles per minute. So the more the isolator deflects, my natural frequency drops, that ratio of driving frequency to natural frequency increases, and my efficiency goes up. Okay. So if I look at a simple example, if I had a piece of equipment operating at 350 RPMs, and I put it on isolators of increasing deflection, let's just take a look, theoretically speaking, how much vibration gets into the structure. What's the transmission? Transmission being the opposite of the efficiency, or how much I'm keeping out, right? So if I put that theoretical piece of equipment on springs that are deflecting 25 millimeters, I'm going to transmit 40% of that energy if I go back to that efficiency equation. If the isolators deflect 50 millimeters, I'm only going to transmit 17%. And if I go all the way up to 125 millimeter deflection, I'm only transmitting 6% of that energy. Now, the efficiency equation gives us some direction as to the effectiveness of the isolation system, but there's some weaknesses to it. The primary weakness, it doesn't take into account the structural deflection. It assumes that the structure is infinitely rigid. But we know in modern buildings, the structure is very flexible, and that can also affect the isolation efficiency. So I'll show you that real quickly with my demonstrator here. Little fan. Nick's just changing the video. So I have my little fan with a massive unbalance. Okay, a little bolt through the fan wheel. Yeah, change it to that.
That's where it is.
Oh, it is? Okay. I'm sorry, I have my little very sophisticated vibration meter here. Because obviously you can't feel the vibration in Italy, right? So a little vibration meter. Let me see if I can get that in the screen. Okay, so if I turn the fan on, it's the most dangerous part of the presentation. Turn the fan on, you can see the vibration created. Okay, here we go. With a small increase in speed, you can see a tremendous increase in vibration energy. So if we go through the isolators, one of the earliest isolators was a cork pad, very limited deflection. The close-up of that little cork sandwich. So if I take my machine and I place it on the cork, because it has a very limited deflection, the performance is not particularly great. You can see that. And of course, the pads are underloaded. The test is kind of rigged in my favor a little bit. Almost 100% transmission. A pad that's a little bit better, little rubber pad, is going to deflect, I don't know, 5 millimeters or so, better than the cork. It's like a little piece of waffle. Again, for the purposes of this test, it's going to be underloaded. It's not going to deflect much. But just going through the hierarchy of isolation, what performs better. You get into little rubber mountings. These deflect, I don't know, 8 millimeters or so. If properly loaded, a little bit more deflection. We'll go through all these. And then you get into steel springs. And steel springs are designed anywhere from 25 to 125 millimeter deflection. Now, it's loud, but you can see the water in the glass is chill. And you reduce the vibration transmission to the structure. You can get into a resonant condition. Try to get there. Resonance now is where the driving frequency is very close to the natural frequency. You get some significant amplitudes there, and you get some significant vibration in the glass, right? But as you get away from the natural frequency, the fan steadies out, it becomes a free body in space, and there's very little in the way of vibration transmission. Got to work on my motor a little bit. Okay, resonance. And when you get it up to speed, there's really no amplitude here. Although the springs are deflecting, I don't know, maybe 20 millimeters, the fan itself isn't bouncing up in 20 millimeters. It becomes a free body in space. The amplitude is minimal. And I'll put it back in the slideshow. So isolation gets fairly complex. It's a very small percentage, as you're familiar, a very small percentage of any mechanical contract. So the problem gets complex, but the typical designer, you don't have a lot of time to dedicate to the proper selection of isolation. So the industry has created selection tables that take into account the various HVAC equipment you might see on a project, as well as the structural deflection. So by knowing the equipment and the structural deflection, you can very easily select the appropriate isolation. So as an example, if we had a pump on a 30-foot span with a possible structural deflection of up to 25 millimeters, we use the selection matrix. And in this case, we're using letters to designate the appropriate isolation systems. In this case, it's B, L, and O. And to the right of that is the recommended static deflection of the isolators. Spec letter B is a freestanding spring. Spec letter L is a concrete base and supported by those springs. And spec letter O is an elastomeric connector. So very quickly, the designer can select the appropriate material, doesn't have to necessarily worry about the efficiency equation or structural deflection. It allows them to do that very effectively. This is what that system looks like in the field. And suction pump supported by a concrete base. And that in turn is supported by freestanding springs. We get into situations, another weakness with the efficiency equation is that when you get into very high frequency systems, the springs often don't work, although the theoretical efficiency will tell you they're going to be very effective. Air springs are effectively a rubber bladder, capped top and bottom, pressurized to support the load. And the beauty of air springs is there's no steel contact between the equipment and the structure. So you eliminate that sound transmission path. Very often used in retrofits where you've had a vibration problem. One example of that is a project we did in California at Twitter headquarters. If you're familiar with the social media, Twitter, now called X, they had a very large centrifugal chiller above their conference room. It was supported on springs, had terrible noise in the space. They replaced it with air springs, and fortunately, I was able to get before and after results. You're all familiar with these type of tables, obviously just the sound pressure level in dB on the left and frequency along the bottom. The gray line on the top is the chiller operating at 100% capacity. The orange is the chiller operating at 30% capacity. And these are all the noise levels taken in the space below that chiller. And the gold line is the noise with the chiller operating at 100% capacity on air springs. You can see it's a tremendous noise reduction, almost 25 decibels. We have tremendous success with air springs. If you have anything that's extremely acoustically sensitive, air springs are the way to go. They also have a role in scientific applications and industry. By increasing the area of the air spring, you can support higher and higher loads, just a function of pressure and area. And if you increase the volume of the air spring, as shown here, you can reduce the fundamental frequency. So these were built to support a large dynamometer at Ford Motor Company. They have a 1 hertz natural frequency. And this frame weighed 1 million pounds, so I don't know, close to 500 kilograms. And on top of this concrete block was a dynamometer used to test cars and determine vibration and noise issues. So they wanted to keep that free of any outside vibration. And that's why the acoustician recommended these air spring supports. One of the tricky things in Italy is you have obviously a significant seismic risk. So seismic and isolation, really two conflicting engineering requirements. With isolation, you want the equipment free floating. With seismic, you want it fixed to the structure. So we have selection tables. This is just a seismic risk map of Italy. I don't have to tell you that you're in a high seismic area. We're all familiar with the quake that occurred back, one of the more recent severe quakes back in 2009, and unfortunately killed more than 300 people. But there's ways we can protect the public from at least any mechanical failure, pipe bracing the equipment. How do I do this? This is a seismic test of equipment real quick. This is a seismic simulator of a cooling tower. So on the west coast of the United States, they require that equipment be tested to make sure it survives the earthquake, and that's what this video showed. This is what's going to happen to an isolated piece of equipment. This is restrained. It's on restrained isolator, so it keeps the equipment captive. It's something that we have to be concerned with. Isolation causes tremendous damage. So we have selection tables that combine the isolation and appropriate seismic restraint. So that same pump we looked at earlier in a seismic zone, we're going to have the same spring mount, concrete base, elastomeric flex connector, but now we're also adding a seismic snubber that does not short out the isolator, but keeps the equipment captive in the event of an earthquake. And that's what that looks like in the field. This is a project in San Francisco on the west coast of the United States, very high seismic risk. And you can see it's a concrete base, and we've incorporated the appropriate seismic snubbers. Pipe bracing as well, something you have to be concerned with. We can do that. We talked about vibration isolation, but as you can see with this fan, it creates a lot of airborne noise. So we have systems, both floating floors, walls, and ceilings, to reduce that airborne sound transmission. Don't really have the time to get into that in any depth, but know that's available, where we can create an isolated room within a room to reduce the sound transmission. And we also have floating floors to reduce impact for areas like gyms, bowling alleys, aerobic rooms, floors, and ceilings. So I'm out of time and probably went over, which is my bad habit. So I'll turn it over to Doug, who will discuss some of the more challenging projects we've conquered in the last few years.
Great, thanks, Jim. Mason Industries has probably 65 to 70 engineers in its employ. Globally, it's 400 people that we have. We have manufacturing here in New York as well as in Thailand, in wholly owned companies. So our supply chain doesn't get impacted by anything but our demand. And the business has grown tremendously as a result. What we want to discuss right now is our engineering capability, and we do quite a bit of building isolation globally and significant structural isolation globally, as well as certain military applications. So I'll jump into that now. Building isolation is a topic that you can look on our website and find everything you need to know. But essentially what we're going to be doing is picking up the structural loads from the structural engineer. We're going to function as part of the design team. We are going to be actively involved in discussing with the architect, the structural engineer, and all the trades, as well as MEP and everything else, how to properly isolate the building and prevent the transmission of noise through the structure. The simple photographs you see here, one is an isolated train platform in Australia. The other one is Zanko Hall at Carnegie Hall. And we have manufactured and isolated, I think, about 80 buildings in total. So it's something that we take really seriously. There's a significant demand to offset liability. We have registered engineers in every state, a couple of foreign countries, not Italy yet, but we'll certainly get registered there at some point. All with the idea is We step into the arena as professionals with the capability to do a significant design. That's page 1 of our list of projects for bridge bearing isolators, and it's significant. First job was Trinity College. And that was the job we did as laminated bearings. We now vulcanize our bearings. We've also developed our own means and methods, which we are welcome to share. Federation Square was the one picture that you saw, but we have a concert hall in Athens. We've done the New York Times. We've done a project which is multi-purpose called 122 Greenwich on Springs, and a number of others. And these are not fully up to date. The design requirements utilize a term called shape factor. All right, and that is the loaded area over the escape area of any given bearing. And what that means is we can generate curves and have a design requirement so we can better design a low stress, low strain bearing so that we can comply with the natural frequency that's necessary and it's not overstressed. Some of the things that people do in error is overstress a bearing in a building isolation project, and that significantly reduces the longevity of the bearing. So low stress, low strain is a concept that we've evolved with, and it has worked 100% of the time. We have our own in-house testing facility, and we're testing, in this case, bearings in compression and bearings in shear, all with the idea that every bearing that goes under a building or is utilized structurally to isolate noise and vibration is going to be tested to 2.25 times the rated capacity. So we are always in an area where we are never going to exceed the capability of the bearing, and we've got a lot of room. So if it does get overloaded, if the structure here is slightly off, we're still within a range of natural frequencies that we want to be, and the bearing is never overloaded. Low stress, low strain is the key. All of our bearings and designs of elastomers are independently tested. And I'm saying that because we don't self-certify. We certify independently at all times because it only makes sense. So in this case, we went out to experimental services and we did creep testing. Creep testing is the additional deflection over time. And basically what happens, it's in decades of time. So you want to get 100-year longevity without any additional settlement. And basically we're working in the thousandths of an inch or mils in this case. So the idea is we don't have a lot of additional settling because of that low stress, low strain requirement. Dynamic stiffness is a key component, and dynamic stiffness is a function of design. The table in the top graph is for neoprene. We've generated our own in-house curves for dynamic stiffness and shape factor for natural rubber. Natural rubber has a much lower natural frequency and is that much better to utilize when you're manufacturing bearings for building isolation. Physical properties are also independently tested, all with the idea that certifying the compound, the independent testing, and the bearing test prior to installation means that there's no liability. We've done our homework. We've done this a number of times, hundreds over the years. At the end of the day, the bearing quality, the testing demand is all there so that we are certified and the bearings are capable of handling the intended load. Last but not least, we check stability on bearings that are tall, and these particular equations were developed for these bearings, which are utilized for the wind farms that were in the North Sea, where they were having problems with vibration generated by those large propellers generating electricity, but there was a vibration issue and seals were breaking that were holding the two components together that had elevated the propellers about 50 meters above the sea level. These bearings solved the problems, and we needed to check stability because they needed a low frequency natural rubber bearing. Lexington Avenue in New York City is home of a lot of buildings that are isolated because the Lexington Avenue subway line goes north-south. And so does Lexington Avenue. This job is 610 Lex. It's a partial isolation project. And along this line, where you see my arrow, is the subway line. And it's no more than 2 meters away from the building face. And these are shear pins to handle horizontal loads. And these are column capitals that support the building itself. Shear pins are designed to handle horizontal wind loads and minor seismic loads so that there's no real significant movement because you've got mechanical systems that are working vertically through the structure as well as elevators and people movers. So it is a major issue. So we came up with the idea of shear pins many years ago to handle the horizontal load, and that's what this element is right here. In reality, it looks something like this. So you're seeing bearings that have been tested. That's those green stickers on each of the bearings. And this area is filled with sand, and that gets removed after the concrete is poured. These are pouring forms that get removed as well. These are the shear pins covered with an elastomeric membrane that's 50 millimeters thick so that it can handle the horizontal loads. And every one of these approved stickers means that each one of the bearings was tested to over 200% of the rated load. So the idea is belts and suspenders, you can't have a failure of any kind in a building isolation project. In this case, it's Bond Street, and if I hold up these drawings, the same, it doesn't even show, but it's the same drawing that you have on the screen, but we generated approximately 30 structural drawings for the construction and installation of our equipment. So the idea was the building is partially over the subway itself. There's no vertical load, there's no horizontal load that can be transmitted to the subway. So in this particular instance, we had bearings that actually slide, and that's what these bearings show. So there's stainless steel interfaces and Teflon sliders on top of the bearings so that the building is free to float on top of the bearings and move as the vibration is generated. So there's no horizontal load that gets transmitted to the structure. The table that you can probably barely read shows loading at 80, 100, and 120% of the loads that we've been given by the structural engineer. And it shows the range of frequencies that will be achieved for railway or for building isolation near railways. It is a common natural frequency range of 6 to 8 hertz that solves the problem. And this is the result of at least 60 buildings on rubber pads near trains. We use shear keys to handle horizontal loads through the elevators, and what they actually look like in practice is this picture that shows the horizontal shear keys here, where there's no steel in place, the bearings that are supporting the load of the elevator chase. And these rods that protrude are there to prevent overturning. So there happened to be, in this case, overturning moments being generated by wind loads that were compensated for as well. Our involvement with the design team the structural engineer, the architect is critical to come to conclusion on a building like this. So it takes a lot of time, a lot of meetings to get everyone to understand how our systems work and how it evolves and solves the problem. This is in Bond Street in Brooklyn. It is 100% successful. It's a hotel, and there's no perceptible vibration above the second floor. That's a structural drawing that we put together for the installation of the Schiavi. One of the more significant projects that we were involved in is the Kirchner Center in Argentina. What's unique about it is that's the edifice of a 125-year-old post office building. That post office building was transformed into a museum. These spaces here were the offices of Juan and Evita Perón when they were the president and the wife of the president, first lady in Argentina. And I was lucky enough to get a tour of the whole area prior to all this construction. The isolated structure is this element right here. It's a 4,000-seat theater. The reason why it's isolated is the train goes right through this space in one direction and behind the structure in the opposite direction. So it's train running east-west and a train running north-south right underneath the building. So they were really concerned, acousticians were truly concerned about potential problems. Here's what that theater looks like in a section. The isolators are here and here. And these are two columns that were isolated that support the entire load of the concert hall. There's a cutaway that was one of the architectural renderings prior to construction. The bearings were in this location in two spots and down at the bottom of this. And that is the finished structure as well. So we've been involved that this job was completed in 2011. And again, there's no room to make mistakes. So there's zero errors and the acoustics in the concert hall were achieved. And there's no disturbance that's being felt by any of the people in the theater at all. And the testing after construction with no people and the trains at their highest rate of movement during the day yielded excellent results. We have a similar installation at Carnegie Hall in New York City for a smaller hall below Carnegie Hall that sits right above the subway line. This is a bearing in place. I think this is a temporary one, right, Jim?
Yeah, we did some temporary support. So we protected the theater above from all the construction vibration. They actually excavated a cavity under this historic theater. So all the vibration, and they actually used dynamite below. And the idea was to protect the historic theater above.
So that's the finished theater at Zankel Hall. It's a 3,000-seat theater directly below Carnegie Hall. We've also done the major theater in Poland in the city of Warsaw. And basically that's, I think that's at least an 8,000-seat theater. And it's right next to an operational train line. So we have done so many of these projects that it's kind of standard for us, but at the same time, it has to be done correctly every time. There's no room for error. So you really have to be aware of the requirements. We work very closely with the structural engineers, and the idea is to get the actual loading, not the factored loading, which is going to be higher, which potentially gives us an unfair lower deflection on our isolators. That being said, last but not least, Sunrise is an 18-story building, typical isolation system. The critical point on this one is establishing the isolation plane. The isolation plane should be above grade so that you don't have any compromising vibration coming through the soil into the structure. So this is at the location right below the ground floor. We would prefer to be above on the column capital at the first level before the second floor. And then we can isolate and not even have to think about the requirements for not having short circuits through the soil. So the isolation plane is a critical term for establishing the bearing location so that you're in a position where you're not compromising the integrity of the acoustical integrity of the structure. It's critical discussion with the architects and the engineers. We do a lot of testing. The founder of the company is in the photograph, Norman Mason. We were bidding a project in in China, in Hong Kong, and it was called the Lyric Theater. And we built and designed the spring required for the project. And then we did horizontal testing because there was high wind loadings due to typhoons, and they wanted to know what the spring constant were and how the building was going to react under the load of high wind. And we established that by doing some independent testing. In this picture, it is a Ferris wheel is what they call them, but it's not a traditional Ferris wheel as we know it. It's a people mover. Each cab can hold 10 people. And we have isolated bearings, structural housings all around the Ferris wheel. And it's between two independent hotel towers at the 40th floor. So the idea was, what type of bearing do they need? What type of isolation efficiency do they need? What deflections required? And we worked on the whole project and basically established the proper design, got it certified, tested, and installed. And that's a typical bearing right there. And that's what it looks like today. So the Golden Reel in Macau is a casino. We've also done the casino at the Wynn property. And another case of people move is typical ski gondolas that go from the casino to the hotel to a zoo. And all of those supports were isolated as well. That being said, I could turn this on, you could look at it, but one of the last things we do is a lot of military work, and this is an isolation pad that's designed for United States Los Angeles class subs, so that submarines, so that there's a singular frequency that the submarine will operate at, and the machinery doesn't call out any specific tones that would make that sub uniquely identifiable. So we have multiple bearings under all the equipment in these US submarines. And we do a lot of military work. A number of years ago, we did a job for Fincantieri, the shipbuilder in Genoa, I think. And it was for the vessel that went across the Atlantic the fastest. And we did some engineering design work for their thermal expansion and isolation required for the exhaust systems of the turbines, gas turbines in the vessel. That being said, I think I've rushed through it a little bit, but we're at about 45 minutes right now. I'm done, and I guess we can open it to questions if you'd like.
Thank you very much, Douglas. Thank you very much, Jim, for this very interesting presentation of related to Mason Industries. I open to the auditory if there is some questions. Now I do not see any question at the moment in the chat room. Just to begin, probably auditory is shy a little bit. I can start with just one question, particularly related to the testing of your system, in particular when you speak about rubber or neoprene and so on. I saw that you perform tests for aging, for example, in temperature by using ozone and so on. Do you perform also tests in creep to evaluate the static
Yeah.
deflection during time of changing?
So we've done creep testing on every variation of our elastomers for building isolation. Long-term creep, I think you're allowed to have 3% additional travel in a typical bearing. That's defined by AASHTO, the governing body in the US. And what we'll do is make that much less than 3%. We'll probably be under 1%. So the low stress, low strain criteria works extremely well. Working with 50 and 60 durometer where the dynamic stiffness is low works very well. That's a dynamic stiffness correction factor of 1.28 and 1.3 respectively. And creep is a significant issue. So anytime we're isolating a railway or a building, we're going to have to be concerned with long-term creep. The typical developer wants a 100-year guarantee. And just imagine that we write 100-year guarantees as a business. And it happens because a developer wants to have a building or a facility be able to last. We recently did a building isolation project in London, and we lifted a 400-year-old building and isolated it with bearings. And it's the only time any building that's 400 years old has been retrofitted. So we work very well with structural engineers, and it solves a lot of problems when we know what we're talking about.
Thank you.
Mm.
We wait for some questions from auditory.
I think we have 36 people looking with 37.
Yes,
No?
it is. There is a very large auditory actually, but I don't know if someone. I speak first shortly in Italy. Potete anche inviare le domande in italiano, poi traduciamo. We translate the question from Italy to English.
No problem. If questions come up, that's great. Our representation is through BBV in Milano. We may have seen our translated architectural engineering guidelines. We have it in Italian. We also have it in Spanish, Chinese, and a number of other languages. And we'll continue to work to get more of our literature translated so that as we grow within the Italian market through BBV, we will have more information readily available for the acoustical group. We work very closely with acousticians. We have evolved the business that way since Norm Mason founded it 65 years ago.
Yes, actually, I have to say that the vibration isolation theory and everything, and material used for vibration isolation theory and acoustic insulation can be actually treated by the same basic theory and be very useful to join the competence from the two groups. So it's possible to evaluate, especially for structural acoustics, to use the same model using vibration isolation theory to evaluate the acoustics, the reduction index of radiation efficiency or reduction of radiation efficiency also by calculating vibration theory. I have another question because it was very interesting relating, for example, to the floating floor. You show us in your presentation the floating floor realized by a spring, for example. What is more or less the weight of this kind of floors? Can be used, I suppose, in dwellings, for example.
The dead load is English system is 50 pounds per square foot for 100 millimeter thickness. But on top of that, we're gonna have live load and equipment loads. So marrying all of that together is, we're gonna ask a lot of questions about what it weighs, what the live load is it a reasonable live load? Do we have an acoustic live load and a structural live load? And what I mean by that is the acoustical live load 20 kilograms per square meter, and the structural live load is 100 kilograms per square meter? We have to get the right live load to design properly, because if the structure, floating floor, whatever the case may be, never sees that load, but it's a required load to design for, we'll accommodate that required load, but we have to work with the acoustical load to get everything right.
Yes. You think that can be considered competitive with respect, for example, typical floating floor by using rubber or neoprene and so on, from the economical point of view? This kind of solution.
So the installed cost, the jack-up system is slightly lower than the formwork system. The spring systems are more expensive than the rubber systems. I could do a quick calculation and get your approximate cost per square meter if that's what you're looking for.
Thank you. There is a question from the auditory. I don't know if you can see the question also, or I read the question if you want. So it's from the question is, can you show some application of large rotating equipment isolation, both by the frame and the connected piping system?
Sure, we do that all the time. What type of equipment? What is the individual interested in?
I don't know, because
for equipment.
We had the one photo of a pump on a concrete frame supported by springs with elastomeric flex connectors in the piping. We do have other photos of installations.
We have a photo library that we can supply pictures of anything that have happened in the last 50 years. So if we could zero in on what that question is requiring, is it a chiller? Is it a pump? Is it a cooling tower? Is it a piping system? We can provide anything that they request. That's not a problem.
Okay, thank you. At the moment, I do not see other question. Oh, yes, there is another one. This is in Italian, so I don't know if you can translate, if you see, because it's very long, I don't know. You see the question in the...
We see it.
They're looking for the difference between EPDM and SBR.
Yeah. And frequency and something about water as well. Can you figure that out? So
They installed for.
EPDM is a great elastomer that's utilized for flexible connectors. SBR is a cheap solution and not an elastomer that we ever use. So if we had 4 anti-vibration components like this, we would manufacture either in bridge-bearing rubber, bridge-bearing neoprene, or neoprene. We'd rarely manufacture an EPDM unless there was a special requirement. EPDM is an elastomer that can handle a lot of various chemicals, and that's why it's utilized most often in flexible connectors. And we do use it in flexible connectors. I'm trying to.
Esiste una relazione, so it's, there exists
315 hertz.
the second to last,
So you know what?
does it exist in a maximum Q equals P12-8
So
and the deflection?
Alessandro, are they talking about vibration through the piping or are they talking about vibration through the structure? Because at that frequency, I'm thinking it's.
I think through the piping.
Yeah, that's a blade passage
wow.
frequency disturbance. So that's best tackled with an elastomeric connector. And if I could go back to the presentation, but when I talked about the pump, we recommended a concrete base on springs that takes care of the vibration from the equipment to the structure. And that elastomeric connector, that's going to knock out the blade passage frequency that they're discussing.
So the 15 dB reduction that's up there, we might be able to get 15. It all depends on the equipment. It all depends on the vibration, but we've done that testing and that's available on our website. I can take that person directly to that. What we'll do is for Fabio is we'll translate the question, answer it in English, translate it into Italian, and give him a specific answer sometime today.
Okay, there is another question related to the Antonio Vicale asked if the vibration in the vibration system used for seismic application, what kind of office is possible to contact from Mason industry to put the characteristics in the calculation.
Federica Sala in BBV should get the inquiry, and she's probably.
Yeah, she's joined us online.
She's joined us online, so she may be able to type in her contact information. Basically, she'll translate it, get it to us, and the combination of seismic and vibration isolation, we have tested independently again for certification in hospitals in the state of California. All of our equipment has what was formerly known as OSHPD certification. So we have put shake tables in use to test our isolators so that we can come up with a rating that is confirmed by OSHPD, State of California, Office of Statewide Health Planning and Development, so that they can be installed in hospitals. So anything that we do that seismically require the requirements, we've achieved the requirements of the state of California for hospitals. So everything that we do survives an earthquake, is what I'm trying to get at. And again, we'll translate this, we'll work with Federica, and we'll try to get you answers to every one of these questions if we're missing a little bit in terms of the translation at this moment. I think Fabio's asking about what?
Yes, he say thank you. Actually, say thank you because he say he agree with you with your answer, because he say that the pipe was longer 5 meter and was at the beginning was stiff, and after the installation of the flexible joint, the pipe become more flexible. So he say thanks for your answer. So
our pleasure. That's great. Do we have anything else that's open, or is that it? I think that's it.
At the moment, there are not other questions, so we are at the end of the scheduled time for the webinar. So I just
we hope,
thank you very much for your presentation, for attending for the attendees that attends this meeting. Thank you very much to Douglas and Jim for their presentation. And so I do hope to meet you also in future in Italy, and you are welcome, of course. So thank you again very much, and also for
thank you. Appreciate being in this webinar. Thank you very much.
Thank you. So now there is the other technical meeting, and scheduled for the last technical meeting will be next week. So I think that Simona can probably introduce this slide. I don't know, Simona, if you...
Sì, è online. La slide è online.
Vuoi introdurre tu l'altro
Sì, il prossimo webinar sarà giovedì prossimo, il 12 dicembre, alla solita ora e a cura del sostenitore d'Acoustics. Il titolo è I suoni a tavola, tecniche e strumenti per la valutazione della percezione sonora.
Ok, grazie a tutti i partecipanti, thanks to all attendees, thanks to the speakers. So I think that we can close this meeting. Simone, I don't know, it's okay.
Ok.
Okay. Thank you again.
Buona giornata.
Buona giornata. Bye bye. See you. Thank you very much. And thank you for the early time
That's right.
for you. Thank you very much. Bye.
Thank you, bye-bye.
Yeah.